Hello, everybody. Welcome to this Thursday's Matter Talk. I'm Nicole, and I'll be your host for today. Thursday's Matter is a weekly virtual meetup welcoming experts from around the globe to explore a wide range of topics that touch on software development and the tech industry as a whole. Today's edition is presented by the Skills Matter and Tweak teams. Before we begin, I'd like to run through a few quick housekeeping items. First, you can find out more about today's talk and our speaker in the link I've added to the chat feature in this webinar. As this talk is being recorded, the video of the talk will also be found on that page as early as tomorrow. Feel free to use this chat feature to leave any comments and learning points, or perhaps just share a little bit about where you're joining us from today. I've seen a couple waves as well, so feel free to keep that going. Should you have any questions on the content of the talk for the speaker, however, please place these in the Q&A feature of the Zoom webinar. These are the questions we will be reviewing throughout the talk, and Cheng will aim to answer them at the end. Only questions added there will be considered. We'll also be posting a feedback poll, just one quick question, following this session, and we'd really appreciate your input there. Finally, Skills Matter is proud to be part of an inclusive and welcoming community, and we do have a code of conduct in place. I will add this link to the chat feature shortly after this as well. Please bear it in mind when contributing to the chat and Q&A features of this webinar. And now, without further ado, we are delighted to introduce Cheng Shao of Tweak, who will be exploring the lesser-known secrets of the GHC garbage collector. Over to you, Cheng.
All right. Thanks, Nicole. Let's see, share this whole screen. Yeah, so is the screen working now? All right, so hi everybody. I'm Cheng Shao, working at Tweak, and for the last 2 years, I have been doing my research project at Tweak.io, namely the Asterisk Haskell to WebAssembly compiler. And naturally, it is a project based on GHC. And along the way, I accumulated a lot of knowledge about GHC internals, especially about its backend and its runtime. So today, I'm going to do a little bit of knowledge sharing about these lesser known secrets of the GHC garbage collector. So the agenda of the talk will be like this. So first of all, we are going to talk a little bit about how the allocation happens in a typical Haskell program. And after we see that, we can talk about how the GC algorithms are at play in the GHC's runtime. We are going to talk about the general ideas behind the moving garbage collection, and then also the generational garbage collection. And finally, we'll also talk a little bit about other lesser known lesser used GC algorithms in the GHC runtime, the mark and sweep and mark and compact algorithms. And after the introduction about the garbage collection algorithms, we'll also talk about some additional facts and tips about GC. Those are the facts and tips that you can actually use in your production Haskell programs. We'll talk about the problem about GC synchronization, and also what is static closures and what they mean for the garbage collector. We'll talk about weak pointers and specifically how to keep a closure alive at a certain point in program. And we'll also introduce the compact regions features, and finally, how to gather statistics about the garbage collector in your program and how to tune specific runtime options about the garbage collection. So here we go. Let's see how allocation happens in a typical Haskell program. So on the left is a fragment of the CMM program dump that is extracted from the GHC pipeline. So as you can see, the GHC compiler does several passes of program transformation before it emits native code. And among them, one of the IR intermediate representations is CMM, which is a rather lower level intermediate language. So this is how the allocation of a heap closure happens in Haskell. We do not have to understand every line of this low-level program for now. All we have to know is that it's grouped into several different basic blocks here. So we can see it is C2HH and C2HR and C2HQ. And these basic blocks can jump to each other. And at the beginning of this program, we are trying to allocate a Haskell closure, which is 16 bytes. So what we are going to be doing is that we are working with some global registers here. So the HP register is the heap pointer. So the heap pointer is, for now, it points to the last word of the available heap space. And also we work with another global register called HPLim, which is the heap pointer limited. It points to the last word of all the available heap space, and it is rather constant throughout the execution of a CMM program. And so the allocation of a Haskell closure typically happens via bump allocation. By bump allocation, we mean we bump the heap pointer if there is enough space in the current heap. And in most cases, the heap check is going to be succeeding. And then the returned HP pointer is the end of the just allocated closure. So so we can see that there is a certain segment of space between the current heap pointer and the current limited heap pointer. So the space between these two pointers, we call them the nursery. So the nursery is in the Haskell program. It is where the typical small Haskell closures are being born. So in most cases, the heap check is going to succeed. And then we can see that the average cost of allocating a Haskell closure is very cheap. It's just testing. It's just doing pointer arithmetic, and then you have the allocation succeeded. But in rare cases where the heap check fails, and then first of all, we are going to suspend the current CMM function being executed because there is not enough space. And then the execution is going to be yielding back to the scheduler, where we are going to be moving to a new nursery. And the new nursery is going to be containing enough heap space. And then later, we are going to be jumping to the exact same point where the heap check has failed and the execution of the Haskell program can carry on. And moving to new nursery does not always mean that actual garbage collection is going to be triggered. But in case that the current heap space is already exhausted, then the GHC runtime is going to be kicking in and do some actual garbage collection to free some space. So here is the typical allocation of small Haskell closures. It happens via bump allocation, which is very cheap in most of the cases. And this is for allocation of heap closures. There is another source of allocation which happens on the stack, and the stack allocation happens in a very similar manner. So we also have the global registers, the stack pointer and the stack pointer limited, which points to the beginning and the end of the available stack space. And if a stack check fails, then similarly, the execution is going to be yielding to the runtime, which is going to be allocating a new stack segment that you can put the new stack frames in. So this is the major source of allocation of small Haskell closures. But of course, there are other sources of Haskell heap allocations in the runtime. So first of all, the allocation of other closures happen via the allocate family of runtime functions. So if you look at the C sources of the Haskell runtime, there is allocate might fail, and there is also allocate pinned. So the point of having these special RTS functions for allocating closures is that they allow you to specify some additional properties. So for instance, we have the allocate pinned function. It's going to be allocating a pinned closure, which means that during the whole life cycle of the Haskell program, the closure address is never going to be moving around. So this is used by libraries like ByteString to guarantee that a certain part of the memory is in a stable pointer that you can pass to foreign programs. And the allocation via the allocate family of functions, they are maintaining their own internal object pools, and they are not reusing the nurseries as we have introduced in the previous slides. So yes, this is how the allocate family of functions work. And do remember that if we are using these from the Haskell land, then this incurs the additional overhead of calling the C functions. So normally for small closures, these functions are not called, but only when you are working with larger things like arrays or byte arrays and etc. These functions are called. And under the hood of the nurseries and the object pools, they are managed by the so-called blocks and block groups. So there is the alloc block and alloc group function in the runtime, and they all manage the blocks, which is sized and aligned on the 4 kilobyte sized. And smaller blocks may also form larger block groups, so that when you are allocating something that is bigger than 4 kilobytes, everything is still going to work. And the nice things about blocks and block groups is that they all have associated metadata called block descriptors. So block descriptors record some properties. For instance, which generation does the closures in this block belongs from, and things like that. And the property of Haskell program is that every dynamically allocated heap object or closure, they all belong to a block. And then we do not have to do the bookkeeping of metadata about individual closures, because that is going to be prohibitively expensive. Instead, a lot of the properties about the individual Haskell closures are recorded in the block descriptors of their blocks. And also a lot of garbage collection operations, as we are going to be introducing later, they are happening in units of blocks rather than units of individual closures. So here is how the blocks and the closures are interrelated. And now we have seen how the allocation happens in a Haskell program. Let's see how the garbage collection can take place. So normally the simplest thing you can do is never perform any garbage collection at all. And in fact, it is one of the algorithms implemented in JVM, because in some cases, you would really like to rule out the influence of garbage collection when you are doing some kind of special benchmarks. But of course, Haskell programs allocate like crazy, and the typical allocation rate can be something of gigabytes per second. So you are going to be running out of memory quickly. So of course, at some point, garbage collection has to kick in to recycle some space for further execution. The most fundamental GC strategy implemented in the GHC runtime is called the moving garbage collection, or copying garbage collection in some literatures. So the basic idea behind moving garbage collection is quite simple. The heap space is divided into two semi-spaces called the from space and the to space. And all of the allocation we have introduced earlier, they belong to the from space. And when the garbage collection is kicking in, the garbage collection is going to traverse the from space, find all the reachable closures, and then going to copy them to the to space. And then the two semi-spaces are flipped. And then the space which belongs to the previous from space is reclaimed for further usage. The basic algorithm behind the traversal of the from space is called the tricolor garbage collection. So tricolor garbage collection is a graph traversal algorithm that marks every closure in the from space with 3 different colors. So the black means that it is a closure in the from space that hasn't been traversed by the traversal yet. And there are 2 basic operations related to tricolor garbage collection. One is evacuation. Evacuation is going to be copying a front space closure to space. And after copying, the closure is marked gray. So gray means that a part of the work related to its garbage collection is done yet, but it's not fully done, because we know that closures may contain references to each other. And it's very likely that after copying from space to space, it still contains some pointers that point back into the from space. And we know that those pointers are going to be invalidated by moving garbage collection. So another step is scavenging. Scavenging is going to scan a gray closure that we have marked earlier, and every field that it points to into the from space is going to be evacuated to the to space as well. And after all of them are evacuated, the whole closure is going to be marked as white. This means that all the work related to this single closure has been completed. And now the overall garbage collection procedure works as follows. We have a set of so-called root closures, which typically arise from the active thread state object and their stacks. And after we add these root objects to the working set, then we repeatedly scavenge all of the closures in the current working set. And scavenging these closures may mean that more closures are being evacuated and they are going to be scavenged. And we repeatedly do this after and until there is no closure going to be scavenged. And then we claim that the tricolor garbage collection has succeeded. There are some nice characteristics related to moving garbage collection. So first of all, it is very easy to implement in the major GC implementations. And also, the time it takes to perform a round of full moving garbage collection is proportional to the size of live heap data. This is very friendly to languages like Haskell because we allocate a ton of temporary object, which is going to be dying very soon. And in the end, when we actually perform garbage collection, there is only a few closures that we actually care about on the heap. So we do not have to traverse every single closure, regardless of live or dead on the heap. We only have to traverse the live ones. So this is a property about moving garbage collection. And in order to ensure that the Haskell programs and the garbage collector all see a consistent view of the whole runtime state, we are going to be doing some things to maintain the consistency. So first of all, moving garbage collection requires the stop of the world. That means that no Haskell threads or in literatures, no so-called mutator is going to be running when the garbage collector is going to do its job. So there are going to be GC pauses when we perform moving GC. And also, when we are scavenging an object, and we have to, there is a possibility that different closures point to the same from space object, and the from space object can only be evacuated once. So when we are scavenging the same reference for twice, we have to ensure that all of the pointers that points to the same from space object is going to be pointing to its to space image. So we achieve that by using the nice property that all of the pointers are going to be aligned on 64-bit boundaries in a 64-bit setting. And this means that there are 3 idle bits in the lower bits that is going to be unused in the garbage collector. So when we are evacuating from space object, we also overwrite the first word of the from space object to point to its address in the to space image, and then we tag the address in the lower bit with 1. So later, when we are scanning the references when doing scavenging, we can check whether or not the first word is tagged with 1 or not. Then if it is, then we directly read it as the forwarding pointer, and if not, we conclude that it has not been evacuated yet, and we perform evacuation as usual. And despite the simplicity that we talked about in moving garbage collector, there is one problem with it. So it is possible that your program is going to be running for a long time, and you may eventually accumulate some long-lived heap data. And it's very wasteful to do moving GC for long-lived heap data, because for each round of garbage collection, these long-lived heap data are going to be repeatedly copied to other fragments of the heap. And then copying these things are not going to be freeing up space in any sense. So this is one major problem with naive moving garbage collection. So our workaround to overcome this is to perform the so-called generational garbage collection. So the basic idea of generational collection is that we group different Haskell closures depending on their lifetimes. So some of the closures may die very early, and some of the closures may retain in the heap for a long time. So we call these long-lived data to belong to old generations of the whole heap. And generational GC enables us to collect the younger generations of the heap much more frequently to claim more data. And for the older generations, we collect them much less frequently because they are more likely to retain in memory. And also, we can try different GC algorithms compared to moving garbage collection, as we have introduced earlier. So the basic problem when the basic challenge when we are implementing generational garbage collection is how do we deal with pointers that is intergenerational, because for younger to older pointers, this is not going to be a problem. So when we are doing generational garbage collection, often we are not going to be touching the older generations, the oldest generations, and we only collect a certain generation of pointers, and also all the generations that is younger than it. So if there exists a pointer which points from the younger generation to an older generation, this is not going to be a problem at all, because after the collection, the whatever pointer that exists in the older generation is not going to be invalidated, right? And but this is not always the case. So it may also be the case that the older generation closures are going to be pointing to the younger generations. So we may ask ourselves why this is the case. There is no time traveling in the GHC runtime, but there do exist possibilities that may generate such pointers, that is mutation. For example, if you are having some mutable references like IOREF or mvars, then later you may have a long-lived mutable reference that points to some Haskell closures that has just been produced in the nursery. That is possible. And also, Haskell is a lazy functional language. That means that we have a lot of funcs in memory. And funcs, you can consider them as write once mutable variables. When the funcs are being evaluated, the evaluation result is going to be overwriting the payload of that func. So that is also another source of mutation. And also, we have the stacks, because in Haskell, stacks are regular heap objects as well. And as we regularly push the stack frames onto the stack, we are causing the mutations as well. So how are we going to be handling the older to younger generation pointers? Because if we do not do anything at all, then after a round of generational GC, some pointers in the older generations may be invalidated, which is not going to be a good thing. So our solution is that for each generation, we do the bookkeeping about a specific data structure called the remembered set. So whenever we are performing the mutation on the older generations, for example, we write to the field of mutable variables, then we also add the mutated older generation object to the remembered set. And as we perform generational GC, not only do we traverse the heap within a certain generation and all the younger generations, we'll also have to look into the remembered set of all the older generations, because they may contain the pointers into the generations, and so they must become the garbage collection routes as well. And in practice, it is the case that not only a small fragment of the older generations are going to be remembered sets, and most of the closures are still going to be immutable at that time. So generational GC happens in the GHC runtime as follows. So besides the youngest generation, which is the nursery and the object pools that we have introduced in previous slides, there are two generations by default. And that is a sensible default, as has been seen in a lot of benchmarks. And as we can remember that the nurseries and object pools are being bookkept by the block descriptors, and the generation data structure is also associated with its own block descriptors, and every block descriptor is going to be having a pointer which points to the destination generation of evacuation, so that later when we perform moving garbage collection, we know that which generation is that closure going to. And now we have talked in the previous slide that another benefit of generational garbage collection is that it enables hybrid garbage collection using different algorithms at different stages of the heap. So for the generation 0 and the nursery and object pools, GHC runtime always handles it using the moving garbage collection, because these closures in these generations are much more likely to die at a young age. So you are likely to reclaim more space by using the moving garbage collection here. And there are also other GC strategies implemented. So for instance, for the oldest generation in the heap, GHC never performs a copying garbage collection. It uses another two algorithms, either mark or sweep and mark and compact. So the basic idea behind the mark and sweep and mark and compact is that you have two different stages of the algorithm. The first stage is mark stack. So we maintain a so-called bitmap for all the for closures in the oldest generation, so that you have a lot of block descriptors and blocks that correspond to the oldest generation, and also you have some smaller blocks and their block descriptors that is a very small mapping related to these blocks. these bitmaps can record 0 or 1 for each individual closures in this generation. And 0 means that the object is dead and unreachable, and being 1 means that the object is live and reachable. So the mark phase is going to be traversing the oldest generation to see whether or not the corresponding closures are dead or alive, and then we mark these bits in the bitmap. And after that, we can either perform sweeping or perform compacting. So by sweeping, we mean that for all the blocks that doesn't contain the live closures, these blocks are going to be recycled or swept for further usage. And by compacting, we mean that we are going to be doing some extra work to move these marked closures around to make them more compact in the blocks. And then we are more likely going to be recycling some more spaces through the compacting algorithm. And finally, there is a nice non-moving concurrent mark and sweep algorithm as implemented by Ben Gamari in 2018. So I don't know a lot about this non-moving concurrent mark and sweep, but in case you're interested, you can check out a video in Hack 2018. It is an excellent introduction into this algorithm, and in practice, it seems to bound the maximum pause time of your production Haskell programs a lot. And finally, another thing about GC algorithms is that some of the steps we introduced previously can be parallelized. So the parallel garbage collection doesn't mean that the mutators and the collectors can run in parallel. They still require some synchronization to stop all the mutator threads so that the garbage collection can do its work. But using a parallel algorithm means that you can utilize all the available CPU cores to do some of the GC work so that the maximum pause times can be improved in this case. So the evacuation and the scavenging steps of the previous moving garbage collection algorithm can be parallelized. For evacuation, we have to guarantee that each worker thread works with its own set of evacuated closures, and no closure can be evacuated twice by different threads, of course. So here we use atomic instructions. For each GC thread, it uses an atomic instruction to try to claim one of the closures in the front space. And once it has returned succeed, then it performs the later operations on this closure. And otherwise, it's going to skip and move on to the next closure. And for the scavenging step, it can also be parallelized. There is a so-called pending block set data structure, which is the blocks in the two space prepared to be scavenged. As we have introduced earlier, the scavenging operation in GHC runtime, it happens in units of blocks rather than units of individual closures. Because you have already copied the closures to a two-space block, then in the two-space block, the closures are very compact. There is no slops between these closures. So this means that you can use a linear scanning from the left to the right on the block content to traverse every single closure in this block. So in this way, we do not have to do a very fine-grained atomic instruction on every closure in the two space. Rather, we just use a mutex to protect all the two space blocks. And each GC thread may claim a two space block in this pending block set. And then it's going to be performing all the scavenging operations in this case. So this achieves a better efficiency rather than using atomic instructions on every single two space object. And so previously, we have introduced how Haskell allocation happens. We have also introduced some typical GC strategies as implemented in the GHC runtime. And now it is about time we introduce some specific tips and tricks about the GHC garbage collection. So first of all, remember that GHC GC uses a stop the world strategy. This means that if you are using the multi-threaded version of the runtime, some degree of synchronization has to occur to ensure that no Haskell mutator thread is being run at this point before actual garbage collection happens. And in practice, people seem to make some mistakes which can make these GC synchronization operation very expensive, because when you are doing synchronization, some threads may still be running, but there are some other mutator threads being suspended that can't be resumed at this point. So a long synchronization time in GC is going to hurt the overall performance. And there are two typical reasons where your user Haskell code can block the GC synchronization operation. So first of all, they arise from the unsafe CFFI calls. So we know that when you are calling an imported C function, you can annotate the import declaration by either unsafe or safe. And being unsafe means that the call is not going to be happening with a lot of bookkeeping, such as suspending the current thread. And it brings higher efficiency, especially if you are calling the C function in a very tight inner loop. But this also means that if your C function is going to be taking a long time before returning, and then a garbage collection is kicked in another capability, and then garbage collection is unable to happen before the C function actually returns. So in this case, when you notice that the unsafe C call is blocking the GC synchronization, you might want to find such a C import declaration and change the relevant FFI import from unsafe to safe to allow the garbage collection to kick in at the right time. And another source of user code which it can hurt the GC synchronization is that there are some times when we write a Haskell function which generates a very tight CMM loop. So this tight CMM loop is going to be jumping through different basic blocks in its own function, but without jumping to the scheduler. So we remember previously that when the Haskell function is trying to perform some allocation, either on the heap or on the stack, it has to insert the logic which performs the so-called stack check and heap check. And having the stack check and heap check means that the CMM function has a chance to return its execution to the scheduler, and the scheduler can then decide whether or not to actually start the garbage collection. But in case of a very tight loop, you do not jump to the scheduler, and then there is no chance that the scheduler can start the actual garbage collection. So for these cases, GHC has a specific GHC option called fno emit yields. So when you enable this GHC option in the module which contains the offending function, this means that GHC is going to be forcibly insert logic into your CMM functions to perform the heap checks. So this means that even if you perform no allocation at all, there is still going to be some chances that the execution is to be yielding to the scheduler, and then GC synchronization can properly occur. And if you want to detect the blocking factors in your Haskell application, then first of all, do keep in mind that some of the mechanisms related to the detection of these long synchronizations is only enabled with the threaded flavor of the runtime. So you have to ensure you either link the executable with threaded or the event log threaded flavor. And also, after you compile the Haskell program, you can use the RTS flag called long GC sync. So this means that if there is a long GC synchronization happened in practice, to standard error, it will print an error message to indicate that something fishy has going on here. Or also, you can use the event log mechanism that we are going to be introducing in later slides. And event logs contain entries related to the startup of garbage collection and the time that it takes for GC synchronization. So you can manually filter through the event log entries to see whether or not such a condition has occurred. Another interesting concept I would like to introduce here is about static closures. And what is static closures? We typically call them CAFs, and so CAFs are the special kinds of static closures, which means that they live in the static region of the memory, and they are thunks. And being thunks means that they may be evaluated later and be overwritten with the result value. And you are writing Haskell programs, so you have a lot of top-level bindings, and some of those top-level bindings may be binded to a CAF. And I have some experience writing a prototypical garbage collector using the GHC memory model as well. And the most tricky thing to handle is CAFs. So the reason they are very tricky to handle is that although they have the name of static closures, but in practice, CAFs may point into the dynamic part of the memory, and also vice versa. Some dynamic closures can point back to the static memory as well. But the problem about CAFs is that for dynamic closures, we have the very nice property that they are allocated on the heap, and the heap is grouped using the blocks, and they have their associated block descriptors. So there are a lot of nice metadata we can keep in the block descriptors, but this is not the case for static closures. So a lot of mechanisms that rely on the block descriptors of the closures, they are no longer effective for static ones. And worse, when the dynamic closures are reachable when using the normal GC tracing mechanisms, but static closures may be referred to by the CMM and C code as well, because each static closures, they have their associated symbols. And the problem with garbage collection is that it can scan the memory, it can read all the block descriptors, the payloads of the closures, and also the info tables as it wish, but it cannot scan the code section of the Haskell program being executed. This is not always possible with certain architectures such as WebAssembly. So we have to ensure that when CAF is being referred to by a piece of code rather than a piece of memory, it is going to be properly traced as well. So the solution is that we annotate the generated code with additional data structure, so that when GHC is going to be garbage collecting a piece of code, it doesn't have to scan the code itself, it just scans the additional data structure. So the data structure in effect here is called the static reference table. So when GHC is doing code generation, it is going to be generating a lot of so-called info tables, and each info table is associated with a CMM function called entry functions, and they contain the logics that we have seen earlier, which perform all your Haskell evaluations. And in order to garbage collect the CAFs reachable by the entry functions, we emit a special kind of closure called SRT, and all the CAFs which is being referenced in this piece of code, they are referenced by the payload of the SRT as well. So now when the garbage collector is going to be garbage collecting a piece of code, it doesn't scan the code segment. Rather, it just follows the references in the SRT object, just like following any other heap data constructor. And then we can ensure that all the CAFs reachable at this point is going to be reachable by the garbage collector as well. And in order to implement the special logics related to CAFs and all the other static closures, we have to implement efficient runtime testing, whether or not a closure is in the dynamic region or in the static region, given its address. So the current way of implementing it in GHC runtime uses the virtual memory management feature of the operating system kernel. So it's called the two-step allocator in the 64-bit systems. So first of all, we use a system called like mmap to map a 1 terabyte sized virtual address space into the current program. It doesn't mean that you actually have to have 1 terabyte sized memory in your laptop. Rather, it just reserves that virtual address space for further usage. And then the higher level allocators, the mblock allocator and the block allocator, they ensure that all the heap space is living in the same 1 terabyte sized address space. So the nice property about it is that it's 1 terabyte sized and aligned on 1 terabyte boundary. That means that all the dynamic pointers, they are having the same higher bits. So we can use a simple bit operation to look at the higher bits of the pointer to see whether or not it belongs to that virtual address space. And if not, we can conclude that it is a static closure instead. So this is the trick in GHC runtime to deal with static closures. Another useful feature that we want to use in practice is weak pointers in GHC. It's also available in some other virtual machines as well. So a so-called weak reference, it refers to a key value pair, but holding the reference to that pair does not necessarily keep the key and value alive. So as long as the key itself is alive, the garbage collector ensures that the value is alive as well. And there are cases where the garbage collector ensures that other than the weak reference, there is no other reference to the key. And then the key and value may get garbage collected. And another nice property about weak pointers is that once you make a weak pointer and then the weak pointer is going to be effectful, even if the weak itself is not reachable via your current Haskell program, because the GHC runtime is going to be attaching the weak pointer to a global list of weak pointers. And you can attach the C functions or Haskell functions as finalizers to weak pointers, making it incredibly useful in scenarios like freeing a piece of foreign memory or closing a database session or these kind of things. So when the garbage collector, as we've introduced earlier, is collecting the memory, it's also going to be collecting a list of weak pointers whose key is already dead. And then all the Haskell finalizers are collected together and they are going to be run in a forked thread. So in practice, I would like to say that the Haskell finalizers are less reliable than the C finalizers in two ways. First of all, Haskell finalizers may throw exceptions. And one thing we need to keep in mind is that the exceptions thrown in the Haskell finalizer routines, they are silently ignored. And so you have to add the exception handling logic if you are very sensitive about it. And also, Haskell finalizers are only run if the garbage collector is really traversing the heap to do its work. And there are cases when the garbage collector isn't kicking in. For instance, if the main thread in Haskell is exiting and the whole program is about to shut down, the garbage collector is not going to be recycle the whole heap space. And then there is no chance for the Haskell finalizers to kick in. So when using the Haskell finalizers with weak pointers, we have to ensure that your Haskell program is going to be working, even though the Haskell finalizers are not run at all. So another caveat that you're working with the weak pointer is that we have to choose the correct key types because GHC is very good at certain unboxing optimizations. So for instance, if you are choosing some short-lived types like ints or doubles, then it is very easy for these keys to be out of scope. So the finalizers may be run too early. And if you are using some more complex objects, for instance, like the thread objects in thread ID or mutable references as in IOREF, you better use the unboxed variant in the data types rather than using the lifted variant itself, because the lifted variant may be optimized away by the unboxing optimization. So this has bitten me in practice, and I hope it doesn't bite you as well. And the usages of weak pointers, as we can see, in some cases, you do not want to use something fanciful as a resource T or brackets to manage your resource. You just want the garbage collector to manage it. So in these cases, you can use a weak pointer for running the finalizers. And another surprising usage of weak pointers is that you can use it to perform some kind of runtime test that whether or not a closure is still alive at a certain point in time. So this trick is implemented by Simon Marlowe, described in one of his blog posts. The basic idea is that, first of all, you create a weak pointer of a specific heap object, and you do not have to attach any of the finalizers of it. And after a certain point of time, you want to see whether or not that closure is still alive. Then you call the perform GC function as in base to trigger a full round of garbage collection. And after that, you can use the interfaces in the weak pointers to see whether or not the key is still alive. So if you implement this runtime assertion that some of the things should be freed after a point, but then you find out that the weak pointer is still referencing that closure, then you can be sure that you have spotted a source of memory leak. That closure must have been retained by some other closure in the heap. So this is another useful place where you can use weak pointers. So in order to keep a closure alive when you are using the weak pointers, so for instance, you are allocating a pent byte array, which is byte string, and you want to prevent it from being collected too early. Or in other cases, you want to ensure that before a certain point in the program, the weak finalizers is never going to be run. Then you have to ensure that the key object is alive at that point. So there are two fundamental approaches to keeping a closure alive. One is using the touch primitive operator. So it is rather lightweight. It's going to be generated to a no-op in your assembly program, but due to defensible optimizations in GHC, it is unsafe in certain cases. So in GHC headquarters, there is also ongoing work to discuss and implement a safer prim-op called with that is going to be used to ensure that a closure is alive when executing a continuation. There is also another mechanism called stable pointers. So the stable pointer concept, it is just an index into the so-called stable pointer pointer table. And this table, you can add new entries by adding any arbitrary heap closures to it. And you add a heap closure, and then you obtain an index into the table. And later, you can pass the index to the foreign world and then fetch it back vice versa. And you can fetch the same heap closure as you registered, because closures in the table, they are registered as garbage collection routes as well. So if you register something as a stable pointer, you can be absolutely sure that it's going to be surviving the GC until you explicitly dereference, you explicitly delete the entry in the stable pointer table. It is rather heavyweight because you have to call in the C functions in the runtime. And also the pointer table is locked by a mutex. So there's also the cost of mutex. So when you want to be really sure, but you do not mind about the costs, then you can use this approach. And also, there is another useful feature in recent GHC versions that I would like to introduce here. It is the compact regions. So we have discussed about the problem of long-lived data structures in heap, that we have the mitigations like generational garbage collection to deal with them. But what if we can group these long-lived data structures together in their own blocks, and we tell the garbage collector, hey, I do not want to traverse this region of memory at all. So that is the basic idea behind a compact region. So the compact region, each region has its own associated blocks and block groups for storing the closures. And there is one property about closures in a region. The closures are self-contained. They may reference each other in the same regions, but we can guarantee that it does never point out to the dynamic region of the memory. So there is no outgoing references. So this allows the compact region to be somehow serialized and then deserialized back, adjust pointers, and then you have a piece of usable memory again. And after you add a certain closure to a compact region, after fully evaluating it, the same region can be used to add new closures to it. So you can use compact region as some sort of cache database sessions. And potential usages of compact regions, other than handling large, long-lived data structure in memory, is that it enables you to do some sort of non-portable serialization. If you do not want to transport your serialized data across different machines, then compact regions may be useful in that case. It is extremely fast. The problem with compact region is that there is no type safety compared to your typical Haskell serialization libraries. And you have to guarantee that whatever referenced by the closure you want to put into a region does not contain things like a pinned byte array or a function closure. So there is a lot of good material about the compact regions online that you can find. And finally, we can see that it is possible to gather the GC statistics from a running program at runtime, and then you can analyze these statistics to find out the bottlenecks. The first mechanism is using event logs. So the event log is, so the basic idea is that the GHC runtime contains the event log flavor. You can link your program against it, and then add some runtime tracing option to run the program, and then you can use a tool like Threadscope to load the log, and then you can see some statistics like how many data has been allocated and how much time GC has been taking. In your Haskell program itself, it's also possible to use ghc.stats in base to gather the statistics about garbage collection. And there is also an external framework that allows you to browse the GC statistics via a web interface. It's called EKG. So in case you write something like a web server, you can use it. And finally, there are different methods to tune some runtime options to improve the garbage collection performance. First of all, we have to keep in mind that there is a basic trade-off between the so-called throughput and latency of GC. So by throughput, we mean that, for instance, if you're running an image compressing program or a compiler, you would like that the most percentage of time is spent on actual work, and GC takes as less time as possible. This is optimizing for throughput. And latency means that, for instance, if you're programming your robot to do a heart surgery for you, you don't want the maximum pulse time to something like 200 or 300 milliseconds, but you can make the robot to take more time to garbage collect than your image compressing programs. So optimizing for throughput, we can increase the nursery size so that the initial garbage collection is less likely to trigger, and it's going to be resulting in less overall GC times. And by default, GHC has the concept of idle garbage collection. That means that when there is no Haskell thread active for some time, it's going to be kicking off garbage collection. And this can be bad if you are writing something like make program in Haskell, because you would like the CPU time to be dedicated to other processes rather than the current process. Then you can use a GC option to disable idle GC at all to increase your throughput. And if you are optimizing for latency instead, then you can enable parallel garbage collection, because as we've discussed earlier, it parallelizes the evacuation and scavenging, and the maximum pause time is going to be reduced, but it adds a little bit of overhead compared to the sequential version. So it's not good if you're optimizing for throughput. And for the oldest generation, GHC uses either mark and sweep or mark and compact. So in overall, mark and compact is going to be reclaiming more space, and a single compacting pass is going to be taking more time than a single sweeping pass. But if you are reclaiming more space, that may actually mean that you have to collect the oldest generation with fewer times. So you can switch between two different algorithms and see whether or not it fits your application. And there are a lot of good references, videos, and blog posts about the topic of GHC garbage collection. And the references I would like to list here is merely the excellent documentation written by the GHC headquarters, its user guide, and also the commentary in GHC Wiki containing a lot of useful information. And finally, there is also a slide called GHC Illustrated, which contains a lot of valuable information on the low-level aspects of GHC. You can search for it on GitHub. And if you would like to examine the garbage collection topic outside the scope of GHC runtime, then the textbook I recommend is the Garbage Collection Handbook, as you can search on Google. So, so much introduction for the secrets of GHC Garbage Collector, I guess. And here is my personal email if you would like to get in touch to ask some more specific questions. Thanks, everyone.
Thanks, Cheng. So we'll open up the floor to questions now. There's a few already in the Q&A feature. Cheng, if you'd like to read them out, and we can capture them.
Of course. Let me take a look.
Sure.
Oh, of course. So let's see the problem from James. Should I click answer live? So the problem from James is, does moving garbage collection necessarily have to traverse the whole graph? Can it just traverse one branch to save time? I'm not very sure about what branch means in this context, but as we've discussed earlier, the point of having generational GC is that you do not have to traverse the whole graph at once. You only traverse the segment of a certain generation and or younger generation beneath it. So I hope that clarifies some point. And let's see, do you know how, so another question from Travis Elster. So do you know how the GC algorithm compares to Bowen GC, which is described as generational with mark and sweep? So I do not know a lot about Bowen GC, but I do know that it is a conservative GC. So by conservative, it means that it does not have a lot of runtime metadata about which words are actually pointers and which words are non-pointers. And GHC is a accurately garbage collected language. We have things like info table to describe these things. So I think that is the most fundamental difference of GC algorithm between GHC and Bowen. And in practice, I would like to say that conservative GC means that you are still going to gradually leak some memory at some point. And I don't know if that is going to be a problem for long-lived applications. Yeah, so let's see. So there is another question from Artem. So there are a lot of complaints about performance of GHC's parallel GC online. Can you briefly explain what can go wrong with it? I heard it may be especially that on a large number, of course. So the point is that you have to keep in mind that the number of GC threads is not always identical to the number of system threads that is performing Haskell evaluation. You can tune the thread number. So in practice, you can have a lot of Haskell capabilities on your 48 or 90 core or 96 core machines. But when it comes to performing garbage collection, once the collector thread number goes high, I don't have that exact number yet, but going beyond 16 or something like that is going to make the synchronization cost very noticeable. So even if you're going to be enabling parallel GC, often you want to choose a small number of working threads, and then you can still have a large number of Haskell capabilities to do the actual evaluation. Yeah, so that is for this question. And okay, from FTS, any experience of GHC 8.10's low latency garbage collector? So I have only tested it on very small programs in the NoFib test suite. And overall, I would like to see there is indeed some impact in the throughput in the NoFib benchmarks. But in your real world Haskell applications, often you do not want to optimize for throughput and you want to bound the maximum pause times. And in that case, the low latency garbage collector can be very useful. Let's see. And let's see. And another question from Aaron. Could you define the distinction between static and dynamic closures? So the distinction between static and dynamic closure is that when you are generating the binary of a Haskell program, you also emit some of the Haskell closures inside the data segments of the programs. So these closures are the starting points of your Haskell execution. And when you are evaluating a Haskell program, more closures may be created when you are evaluating these static closures. So I hope this clarifies a bit about what is static and what is dynamic. And are there examples of static closures other than calves? Of course. So if it is not a thunk, then it is not a calf. For instance, you may write a top-level binding, which is a fully applied data constructor. For example, fully evaluated list or something like that. In that case, it is not a thunk, then it is not a calf, but it's still static. Yeah. So why does GC call okay, another question from Artem. Why does GC call returns to the very beginning rather than the actual allocation code? It will do HP bumping again. So yes, it is going to do HP bumping again. The point is that when the garbage collection finishes and it jumps back to the exact same function, it's going to be jumping to the exact site that the CMM function is attempting to do a stack check, heap check. And then because we have moved the heap pointer and the heap limited pointer, then we can guarantee that there is already enough space in the nursery. And then it's going to perform another round of tests, and this time it's going to succeed. And the execution of the rest of the program can continue. Okay. And another question from Jeremy. Can you compare GC algorithm in GHC with those virtual machines like Oracle Hotspot? I have to apologize that I am not expert in the JVMs and the garbage collection algorithms implemented in those. But there are some things to keep in mind because Haskell and Java are very different languages. So in Haskell, as we have seen earlier, I have said that the older to younger generation pointers, they are a problem for generational GC, but they are not very common because of the because Haskell is mostly a pure language, so that we can use the remembered set trick to deal with that. But in Java, you have a lot of mutations, and this kind of intergenerational pointers is much more common. So they have specific tricks to ensure that this is not hurting their garbage collection algorithms. So this is one example how the language design is actually influencing the design of the virtual machines as well. Yeah. So so much.
Thank you, Cheng. Yes, thanks so much, and thank you for that informative talk. Thanks everyone for the discussion after and for all your questions as well. If anyone has further questions for Cheng, please reach out to him directly. His details were on his slides, but also you can find out more about him in the event link. Thank you again, Cheng.
Yeah, thanks, Nicole.
So we're just going to move on to our upcoming sessions. I'll just bring this up for you as well. Great. So our next Thursday's Matter will be next week, same time, with Julian Londier of Zenica, who will be sharing with us a new cloud code tool. Here's a quick look. Feel free to take a screenshot or note it down. We'll also have another talk from the Tweak team in a couple of weeks with Richard on OCaml, so be sure to join us for that as well. As for now, thank you everyone for joining, and I'll put up a quick poll in a minute for your experience today. And we'll see you next time.